The glider project for this class required students to design, build, test, and iterate on a handheld glider design. This project lists certain requirements. The glider had to reach 20 feet, had to be propelled only by the throw, had to fit into a 16 by 16-inch box, had to be shaped like an airplane, and could not break on flight. My design process for my glider, called R27, started by narrowing down these goals until I could get concrete physical requirements for the glider. I wanted to maximize distance traveled, so I sought minimum weight, minimum drag, a high static margin, and an aspect ratio of about 8. I also wanted to be able to make two gliders to prototype, so I initially restrained myself to 12 by 12 inches. To figure out what minimum drag meant in concrete terms, I had to evaluate the different types of wing shapes. I considered 4 design alternatives, being elliptical, rectangular, tapered, and swept forward. Here's a pro and con table I set up to decide which wing shape to use. And since the only two wing shapes with the pro of reduced drag were elliptical and tapered, those were the two that I mainly considered, because that was one of my design goals. In the end, I ended up choosing tapered just because it was easier to manufacture than elliptical, because straight lines are easier than curves. I also considered alternatives for how to hold the actual glider together. I could cut indents into the fuselage and then glue the wings into the indents, 3D print a piece that fits over the fuselage and allows for a wing to slide in, or just flat gluing the wing onto the fuselage. I felt that gluing was not robust enough for this project, so I decided to go with the 3D printing route. However, while prototyping, it became apparent to me that glue and tape worked perfectly well for this project, making 3D printing unnecessary. In addition, I had never used CAD to this scale. Hence, the ease of using these adhesives, as well as their effectiveness for this project, outweighed the con of not being as robust as a 3D printed design. I also considered various alternatives for a dihedral angle. I could have no angle, I could have an angle made by two sides of the wing held together with a 3D printed part, or a dihedral angle where the wings are glued into angled indents in the fuselage. The pros for no dihedral angles ease in manufacturability as well, while the con is no roll stability. The pros for the dihedral angle achieved via 3D printing is a robust design, accurate and symmetric angle on both sides of the wing, and roll stability, while the con was that 3D printing such a piece was likely outside of my capabilities. The pros for the angled indents are roll stability, while the cons was that it would be difficult to get the same dihedral angle on both sides and the indents would be somewhat difficult to make. I decided that rather than deal with the issues of building the dihedral angle, I could achieve roll stability elsewhere. I also had to decide on sizing. I decided to go on a 30 centimeter long wing and 30 centimeter long fuselage. This gave me an aspect ratio of about 10, which is ideal for my design. To size the vertical tail and horizontal stabilizer, I researched and realized that the horizontal stabilizer should have 1/4 of the area of the wing, and the vertical tail should have 1/10 of the area of the wing. This is how I got the dimensions of a tip chord of 1 centimeter and a root chord of 2.2 centimeters, and also a horizontal tail span of 10 centimeters. Also for the vertical stabilizer, I went with dimensions of 2.5 centimeters and 4 centimeters for the vertical stabilizer because this came out to having about 1/10 of the area of the wing. I tested the dimensions I had decided on, but didn't reach farther than 10 feet and encountered nosediving and flipping in the air. This led me to conclude that I was not generating enough lift, so for the next test, I increased the width of the wing. This did virtually nothing because this screwed up my aspect ratio, which wasn't helping. Therefore, I extended the length of the wing to 40 centimeters, the root chord to 3.5 centimeters, and the tip chord to 2 centimeters. This did mean I had to exceed my 12 by 12 inch requirement, but it made the plane or the glider fly better, so it was worth it. I also noticed roll stability issues, so I increased the size of the horizontal stabilizer. It was now 15 centimeters long with a root chord of 4 centimeters and a tip chord of 1.5 centimeters. This new design yielded much better results, but would sometimes fall short of 20 feet. To fix this, the vertical stabilizer went up in size, and it was a triangle with legs of 4 centimeters and 6 centimeters. This was done because increasing the area of the main wing necessitates a bigger area on the vertical stabilizer. This yielded good results, and I decided to stick with this design. And here is a pic of the glider inside the 16 by 16 inch box. My final design had a center of gravity located 2.8 centimeters behind the quarter cord. In addition, my coefficient of lift was 1.88 and my coefficient of drag was 0.303. Lift was calculated using C equals 2W, 2 times the weight, over the air density times velocity squared times the wing planform area. For drag, I calculated induced drag using the coefficient of lift squared over pi times the efficiency factor times the aspect ratio. I then doubled the induced drag to account for zero lift drag because they're supposed to be roughly equal, and then I used this value as the drag coefficient. And here's the video of the throw.
Recording before you leave. That'll work.
My throw reached about 25 feet, indicating that the design changes I made were successful. In the end, the minimum requirements for this project were all met. Overall, this project was very educational. I had a chance to engage in the design process for myself, learn some CAD skills, learn how to apply math and aerodynamic principles to my design. As far as improvements go, I can improve the static margin. The reason that my glider was unable to make its sizable distance was because its center of pressure was in front of its center of gravity. And I did not realize this until after the flight. Pushing the wing back slightly, and adding more weight to the front of the glider would allow for the center of gravity to push in front of the center of pressure and therefore stabilize the glider. Lastly, the resources I consulted when making this glider and report were the FAA Glider Handbook, the Milwaukee School of Engineering Glider Design Packet, the Museum of Aviation Glider Tail Design Worksheet, and Cornell's course that teaches aerodynamic background.